This is how we normally think of an atom. Nucleus in the middle, electrons rotating around the outside like planets. Let's check a fat textbook to see if this is correct. Yep, looks about right, but let's measure it. The nucleus is 1 millimetre and the diameter of the electron shell is 2 times 12.5 millimetres or 25 millimetres. So the electron shell is exactly 25 times the diameter of the nucleus. I'll scale it up, keeping the 25 times ratio so we can see it on the glass screen. Now, also according to the fat book, the nucleus has a diameter of 1 times 10 to the negative 15 metres, and the atom, the hydrogen atom, has a diameter of 1 times 10 to the negative 10 metres. So that ratio is going to be 1 times 10 to the negative 10 divided by 1 times 10 to the negative 15, which is equal to 1 times 10 to the positive 5, which is 1 5/0, 1, 2, 3, 4, 5, which is 100,000 as a unitless ratio. This is not 25. The figure of 100,000 is correct. It is impossible for a text to make a diagram this large on a page. It's instructive to increase the diameter of the nucleus to 1 metre. This means that the closest electron will be 50 kilometres away. To get a good look at this, we need to go and find a mountain. These are the twin peaks of Mount Shinkogan. The closest one will be on the circumference of our 50 kilometre radius circle. Now we're on the pinnacle, 50 kilometres away in the Border Ranges National Park. There are the peaks, and here's our 1 metre ball for comparison. This is a satellite view of our atom. The most notable feature is that it's all space, almost 2 million acres of it. It's very obvious from this perspective that it's impossible to produce a scale model of the atom that will fit in a textbook. The big question is, where's all the mass? Since the electron is very tiny, it must reside in the nucleus. So how massive is the nucleus? To see how massive a proton is, we can do a thought experiment by calculating how many protons will fit into a 1 centimetre cube and then calculating the mass. The edge of the cube is 1 times 10 to the negative 2 metres, or 1 centimetre. The diameter of the nucleus is 1 times 10 to the negative 15 metres. Therefore, the number of protons along the edge is 1 times 10 to the 13 protons. If we cube that number, the total number of protons in a cube is 1 times 10 to the 13 cubed, or 1 times 10 to the 39 protons. This number is 1 duo decillion protons. In other words, lots and lots. All we need to do now is to multiply the tiny mass of the proton by the number of protons in the cube. This calculation is correct, but produces an astonishingly large mass. We'll take this 1 centimetre cube back to the mountain for comparison. The whole mass of the mountain is condensed into this 1 cubic centimetre.
That's amazing.